Hey everybody, Peter Zeihan here coming to you from Colorado on a chilly morning. We're taking another item from the Ask Peter list. This is about quantum computing. How soon do I think it's going to be here, and how do I think it's going to change the industry? To explain that, I need to talk about what quantum computing can do before I talk about what it can't do. So the best way to do that is to compare it to how we do semiconductors currently. So the technology for semiconductors, as we currently understand it, is roughly a century old and rooted in the transistor. The idea you can have an electrical switch that can open or close, which gives you an on and an off position. And as you add more transistors, you add more individual units or bits with on and off positions. So if you have one, you have two states. If you have two, you have four states, because one can be on, one can be off, the other one can be on or off. If you have three, you get 8 states, and on and on and on and on and on. And the technology, since it first went into silicon, 50 years ago now, it's all been about fitting more and more transistors, more and more bits onto a smaller and smaller item. And we have reached the point now that your typical laptop computer, in terms of its processing capacity, has 1 billion or 2 billion bits in it. And if you start including the memory, then the number goes up to 10 billion, and even in some of the higher ends, more than 100 billion. The problem is as we make these things smaller and smaller and smaller, they're getting more and more difficult to manufacture. And we can see within a few years that we will be approaching a hard physical limitation where the individual transistors are approaching atomic size. And once that happens, you're not going any smaller. So the concept of Moore's law, that the processing capacity and the memory capacity doubles every 18 to 24 months, we're coming against a hard barrier there. There are other ways that computers can be improved with, say, heat management, for example, or maybe stacked laminates in your processing units instead of flat ones. But we're still ultimately approaching the point where we can't get much better than we are now. Now, that's not immediate. That's a decade from now, and that assumes a lot of other things go right. But there is a theoretical upper limit, and we can see it from here. That's where quantum computing comes in. Instead of working at objects that are greater than the molecular level, it instead works at things that are smaller. Now, it comes down to the anatomy of an atom. You've got a nucleus that has neutrons and protons, and then you have orbital shells that have electrons. And what a quantum computer does is it adjusts, holds, and measures information in a quantum state of the electrons. Now, electrons can be almost anywhere within their orbital shells. They can be moving in any direction within those shells, and they can be spinning within those shells. And each component of those is a potential bit of information. So if you have an infinite number of locations, an infinite number of velocities, and an infinite number of rotations, in theory, one qubit, quantum bit, can hold more information than the world's biggest supercomputer. And if you get a computer that has more than one qubit, then you're talking about something that's really special. The practical applications of this are endless, but a few things to keep in mind. Number one, we're not that good at quantum mechanics yet. And so even if we're capable of encoding the information, one of the basic principles of quantum mechanics is if you're observing it, it's changed. And in doing so, it changes our perception of the data that has been stored. It's still there, but until our understanding, our practical command of quantum mechanics improves, there's some limitations here on how much we can do. So it's nice to say that there's infinite storage capacity. The practical application is limited by our understanding of quantum physics. Second, there is no way to manufacture these machines at present. They are basically handcrafted, and no two are the same. No two even have similar pieces. So everything has to be assembled and very, very, very meticulously maintained day in, day out. This is not the sort of thing you're going to put on a server farm. It's certainly not the sort of thing you're going to hold in your hand. And until our manufacturing processes can catch up to our understanding of quantum mechanics, and our quantum mechanics can catch up to what actually the system can do, this is something that is going to be in a research lab and very few other things. At the moment, I will grant you that the advanced quantum computers that have been crafted today, not manufactured, crafted, do hold up against our best supercomputers. But they can only be made one at a time, and so there's always going to be the problem of scale. And once we solve the problem of scale, then we can start talking about the materials that are required to build them. We understand the restrictions of traditional semiconductors. We don't yet understand the mechanical restrictions from a materials input point of view of quantum. And I can't give you a time frame for that because we are pushing the boundaries of theoretical knowledge here. And it might just come to a crapper, or it might be the next big thing. We just don't know yet. But it's some fascinating technology that uses a branch of physics that until now has been pretty boring because it's all been theoretical. But it is starting to bit by bit by bit, or qubit by qubit by qubit, enter the real world. And if it works, even if it is just limited to the supercomputer space, the implications for materials processing and data processing is just absolutely massive because these things will be able to imagine the future in a very short period of time. Of course, then it's up to us to build the future with that information, but, one miracle at a time. All right, take care.